For the last section of this topic, we need to look at the equations for resistors in series and in parallel. We will also look at ammeters and voltmeters and potential divider circuits. So we need to look at resistors in series and parallel. So the idea is that when you have many resistors in series, each one has a potential difference across each one, and these potential difference drops add up. There's V1 against this one, V2 across this, V3 across this. All together they add up to a large value for V. The current going through each is going to be the same. It's the same loop of the circuit, so the current will be the same. We know that V is equal to IR for this section and this section and this section. The voltages might be different because the resistances might be different, but the current will be the same. So what is the equivalent resistance of three resistors in series? Basically, we look at the potential difference drop across each resistor and we add them. We add the voltages across each resistor. So in other words, the total voltage is a voltage across the sum of the resistors, the sum of the voltages across the resistors. And we know this is equal to IR for each of the resistors and is equal to IR, where R is the equivalent resistor. Now we can divide by I and we end up with the resistance. The total resistance is basically the sum of the resistances. There's nothing simpler than this. So we simply add the resistances together. So this is in series. In parallel, it's a little bit more complicated. Of course, the current is going to be different, but the voltage, the potential difference across this resistor is the same as that one across there, as the same as that, and that's the basis for the equation for this. Okay, so what is the equivalent resistance of three resistors in parallel? This time we have to consider the current passing through each branch. The current through there is equal to plus the current through there plus the current through there. If we add these currents, it's basically the same as the current that's going through the combined resistance. So this I is equal to I1 plus I2 plus I3. But we know that I is equal to V divided by R. First of all, V divided by R for this I is the voltage divided by the potential difference divided by the equivalent resistor is equal to V over R1 for this resistor and for V over R2 for this resistor, and so on. So we end up with this. Now we've got a common line here. Each one has got V, so we can basically divide by V, and we end up with 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And this is the equation, the formula for resistors in parallel. So we must add the reciprocal of the resistances to get the reciprocal of the equivalent resistance. So when you add the reciprocals of the resistances, you don't end up with the resistance, you end up with the reciprocal of the equivalent or the total resistance. Now we'll do a quick example of this. Find the equivalent resistance of two 6 ohm resistors, and I'll show how to do this, and then I'll show you when people make the mistake where they don't fix the problem. So the resistors in parallel, we know that we must add the reciprocals. In other words, 1 over R, which is the equivalent resistor, is equal to 1 over 6 divided plus 1 over 6, which is the same as 2 over 6, which is 1 over 3. So in other words, we have 1 over 3. So we say that the resistance is 1 over 3. Wrong! This is sometimes just left like this, and this is wrong. This is a fail. This is not the resistance, this is the reciprocal of the resistance. So this is 1 over R, so we need to flip this, and we need to flip that. Yes, so it must be inverted, or flipped, let's say. So 1 over R is equal to 1 over 3, therefore R is equal to 3 ohms. Notice that the equivalent resistance is 3 ohms, basically, why is the equivalent resistance smaller than these two resistances? Well, since we have two routes for the current to go through, it becomes easier. It's like doubling the cross-sectional area, so the combined resistance is smaller. Describe the use of ideal ammeters and ideal voltmeters. Ammeters, they must be connected in series with the components in the circuit, and they should have zero resistance. They need a little bit of resistance to make them work. There's a needle that moves across the dial, and it needs electricity to make that actually work, but there should be a minimum resistance. Zero is ideal. Voltmeters are always connected in parallel with components in the circuit, because the voltmeter finds a potential difference, the energy difference. It must go from one side to the other. So it finds this difference in energy, how much energy per coulomb is lost across a particular component. They also have a very high resistance. An ideal resistance is an infinite resistance. So you never connect voltmeters in series with components, because it will block all the current. Sometimes you will be told that the voltmeter has a resistance of 10,000 ohms, which in usual circuits is almost infinity, which means it will only allow a tiny current through. But this will be insignificant unless the other resistances are also large, and we'll look at an example of that now. This is a 10 ohm resistor, this is a 10 ohm resistor. The voltmeter here is 100,000 ohms. So really, when you combine these two resistances, it's still 10 ohms, because this is such a large resistor. It's going to be off the scale. You can do a quick calculation. Find these resistances, these reciprocal resistances. 1 over R is equal to 1 over 10 plus 1 over 10,000, 100,000, sorry, and you'll end up with the value for 10. However, if we have this kind of circuit where 6 volt drop is across here, we know that this is going to be 100,000 ohms, this is 100,000 ohms, and so is this one. Looking from this previous example, we know that 100,000 ohms and 100,000 ohms are going to have a combined resistance of 50,000 ohms. So now what we have is 100,000 and 50,000. So this potential difference drop between here and here will go over 100 and 50. So this will be basically 4 volt drop across here and a 2 volt drop across here, because this has a resistance which is similar to this one. And you can do that. You can find out what is going to be the combined resistance of these two resistors. The use of the potential divider. Now, what we do is that we use this thing called a potential divider to divide up this potential drop. If we go from there to there is a drop of 10 volts. This is a little more than halfway. So the voltage across this bulb, which will be the voltage from there to there, will be around 8 volts. So this resistor divides up the potential from 12 down to 0 according to where this arrow, or this a flying lead, touches the resistor. Here we have another example. This is 3 volts. So there will be a potential of 3 volts there and 0 volts there. So where is this connected to? This is roughly halfway. So from there to there will be a potential difference of 1.5 volts. So there will be 1.5 volts across here. If we move this to the top, there will be 3 volts across here. If we move this close to the bottom, let's say here, there will be 1 volt across this bulb. Explain the use of sensors in potential divider circuits. You should know about light-dependent resistors, negative temperature coefficient thermistors, thermally dependent resistors, and strain gauges. This is a light-dependent resistor. If we have 12 volts across here, and let's say these are comparable voltages, comparable resistances, this will be half the voltage there. But let's say when light falls on this, the resistance of this one goes down. So then this will have a much larger share of the potential difference, because it will have a much larger resistor, because this resistance has gone down. When now light shines on an LDR, since it's not a normal conductor, it's a semiconductor, it frees up some of the electrons, which allows it to conduct much better. So this LDR will conduct much better. It will have a much lower resistance. So when light shines on this voltmeter is going to read a much larger value. If it was set up this way, when the light falls on this LDR, the resistance goes down. So this is going to have a much smaller share of the output voltage. And this is a graph which shows you how the resistance changes with the light intensity. So on a bright day, we have a value of 100. The resistance is basically 0.1 kilo ohms. On an overcast day, the light level is 10 lux. It'll be about 1 kilo ohm. And then indoors, we have a let's say 10, maybe 100 kilo ohms resistance. A thermistor is a negative temperature coefficient thermistor. It's called negative temperature coefficient because usually as the temperature goes up, the resistance goes up, like a filament lamp. Here, however, as the temperature goes up, the resistance comes down. Now again, this is another semiconductor, so it works a little bit the opposite the way you might expect. So here's an example of a thermistor. We have 0 and V out here, so we put a voltmeter across this resistor. So in other words, when it gets warm, this resistance goes down and this voltage across here will go up. Because this is a small resistance, large resistance, this takes a much bigger share of the potential drop. Okay, this is basically a strain gauge. What we have is this is a conducting material onto some kind of another substance here, which can be stretched or squashed. When you have tension stretching this, basically the increases the resistance of this component. If it gets squashed, then it reduces the resistance.